Well, it's time to do some practice with problems which involve understanding critical points, max and mins, and absolute max and mins. So as always, try to do as much as you can on your own, and then use the videos as a guide or as a supplement. It's very useful, for example, if you get stuck, to get to the point where you're stuck and say, what should I do next? And then once you see it, you're like, oh, let me pause the video, and then let me try it to keep going on my own. The more that you can do by yourself, the better you're going to become, and you're going to be great. All right, well, let's begin. So, our first problem. For the functions shown below, label all the absolute, local, max, and min. And, okay. So there's really two things, absolute versus local and max versus min. Since we only have the pictures to go by, it's okay if we just use the pictures as our guide. So let's start with just saying the absolutes. So we have two functions. We'll do them both at the same time. So the absolute says what is the largest possible value, or the smallest possible value. So for the first one, we can say, hey, this point up here, this is an absolute max. All right, because no output of the function is larger. And similar here, this is an absolute min, because no value of the output is smaller. So we can just we're looking at the output and saying, what's the largest output we get? What's the smallest output we get? Now for the other function, we see, hey, what's the largest? Well, it's at the top of the hill. In fact, it's oftentimes it can be you think, oh, yeah, the absolute max is kind of at the top of a hill. And similarly, like the absolute min is like kind of at the bottom of a valley. So there we go. All right, and so here we go. There's the absolute max there. And now, how about the absolute min? Well, certainly it seems to be over here if it's anywhere. But what's the problem? See, we'd like to say it's right there, but notice this circle. It's an open circle. An open circle is indicating that this function is not defined at this point, but it's defined just below it. Now, what does that mean? Well, the problem is we can't ever get to that value, but we can keep getting closer and closer and closer. It's, you find it kind of have that language of limits. It's like we're getting closer and closer, but we can't actually get there. So for this function, there is no absolute min. All right, good. Now, those are our absolutes. So let's switch gears and let's talk about our locals. So we're going to color code here. So we'll use our blue color here. This is going to be our local max, because we might have several. And we'll use the red color to indicate our local min. All right. So let's proceed. Let's talk about our max. Well, let's start with the first one. So local max just says I'm bigger than everything nearby. So notice if I'm an absolute max, I also have to be a local max, because if I'm bigger than everything, I'm certainly bigger than everything nearby. So there's a freebie. Now, in addition, we can say, well, that's a local max and that's a local max. So we have, in this case, 3 local maxes. And for this function, what do we have? Well, again, absolute min, that's a freebie. Anything that's an absolute min has to be a local min. And then we see one here. Anything else? Okay, make sure you check the endpoint. So you see this endpoint? It is a local min, because what happens? Anytime I perturb, well, the only way I can perturb is towards going to the left. I have to go up, which means I'm smaller than everything you can plug into the function nearby. I don't have to worry about what happens on this other side, because it's not part of the function, as is this other point way over here. So we see that this has 4 local mins and there are 3 local maxes. Now, let's get to our other function. All right, so, well, there's a couple of things that are easy to spot. Certainly our absolute max, that's also a local max. Our endpoint here, you see how it's coming up? That's going to be a local max as well. So we have those two. And I claim there are a couple of more. Where? Well, do you see this flat part of the function? Remember the rule for being a local max or local min. It says I have to be greater than or equal to everything nearby. Now, if you're flat, then if you look nearby, everything's the same as you. So you're equal to everything nearby. So by the definition, we are going to be at a max if we're on a flat segment. At least it's a local max. Now, let's sort of look at the end of the flat segments. Are we at a local max on this left end? And the answer is no, because notice I can perturb by going up. So it's not a local max here, so I'll draw a little circle that's open, but I'm local max all the way. How about this end of the circle? Excuse me, this end of the line. Yes, because notice if you perturb, you go down or you stay the same. So we do include that end. Now, what about the local mins? Well, we see a good local min here. That's easy to spot, the bottom of a valley. But let's come back here. Do we have local mins as well? Yeah. See, if you're flat, then you're both a local min and a local max. But now the endpoints switch behavior. So at this end, you are a local min, whereas you go to the other end, you're not a local min. So I should say, it's hard to tell from that picture because my pen is a little bit too big. So at this point, I'm going to just elaborate. So this is a local max, not local min. And over here at this end, we are a local min, but not a local max. And there we go. And then we have everything in between. All right, well, there we go. There's sort of our intuitive, trying to understand, okay, what is an absolute max? What is an absolute min? Trying to make sure we understand what these things look like. All right, well, let's try another problem. So for our next problem, we're going to list all the critical points of a function. So we have this function, g of x, which is x to 2/3 times 5x squared minus 8x minus 40 plus e to the pi. All right. So, well, what do we have? Well, what don't we have? Let's start with that. Do we have any boundary points? And the answer is no. This function does not have, we're not said to go between, 0 and 5 or whatever. So there's no boundary. So you always remember, look for boundary because we include those as critical points. On a side note, some books say boundary points are not critical, some do. I like to think of them as critical because for me, critical is where the interesting things happen. And boundaries can be interesting, so we want to pay attention to them. All right, well, so how do we find the rest of the critical points? Well, the other critical points are looking at the derivative and asking ourselves the question, was the derivative ever undefined or is the derivative ever 0? So we want to take the derivative. Now, notice that we have x to a power here, then we have a polynomial, which really is combinations of x's to power. So I think a good first step is before we take a derivative, let's distribute this power of x through. So we could have written g of x in the following way. So 5x, now I'm going to add 2/3 to 2. So 2 is 6/3. And then I add 2/3 more, that would make that 8/3. Then minus 8x, x to the 1 is x to the 3/3 plus 2/3 is 5/3 minus 40 x to the power 2/3 plus e to the pi. Now we're ready to take our derivative. All right, so g prime of x is, well, 40 over 3 x to the 5/3, right? Because what are we doing? We take the 8/3, we bring it down. And so that's where we get 5 times 8/3 is 40/3. Subtract 1 from 8/3 is 5/3. Minus 40 over 3 x to the 2/3. Then here, this last one, it'll be minus 80 over 3, because the 2/3 comes down times 40. And then it'll be x to the minus 1/3, because we keep subtracting 1. Now, the derivative of e to the pi. So this e to the pi, you see them keep doing this over and over again. And the reason they do it is because they keep catching people making the same mistakes over and over again. What's the mistake that people might make? Well, the mistake people might make is saying, oh, e to the pi. The derivative of e to the pi is like e to the pi, right? Is it? See, we mix up some rules sometimes. The derivative of e to the x is e to the x. And so people often have a reaction, oh, derivative of e to something is just e to something. Well, be careful, be careful. What's true about e to the pi? It's a constant. And the derivative of a constant is 0. So, gone. All right. Now, we need to ask ourselves some questions. When is this 0? When is this undefined? So I think we need to really get a better understanding of the function, which means to me, I want to clean it up. So I look at them and say, well, the constants all involve 40 over 3. So notice that 80 over 3 is divisible by 40 over 3. So I'm going to factor out a 40 over 3. And then the other thing is, they all involve powers of x. So let me pull out the right power of x. So which is the right power? Well, what we do is we look at the exponents and we ask ourselves the question, 5/3, 2/3, or negative 1/3. Among those exponents, which one is lowest? So we want to pull out the lowest power. So the answer is the negative 1/3 is the lowest power. So we're going to pull out x to the negative 1/3. Once we've done that, what will we have? Well, so if we're pulling out x to the negative 1/3, it's equivalent to adding 1/3 to every power that's left. So here, I'm going to get up to x to the 6/3, which means it'll be x squared. And I grabbed the 40 over 3, so the coefficient is 1. Here it'll be x to the 3/3, because why am I saying 3/3, right? Think of it this way. I'm going to take 2/3, subtract what I pulled out. So 2/3 minus 1/3. All right. So then x squared minus x, and then this will be, finally, I pulled out 80/3, 40/3 coming out of that would leave us with 2, and I already grabbed the x to the minus 1/3. Now, does x squared minus x minus 2 factor? Well, probably, because that seems to be what happens with a lot of our problems. And it actually does. This is one that's not too unreasonable. What I need is two numbers that multiply together to produce negative 2, but add to produce negative 1. Well, it won't take you long to come up with two numbers that do that, x minus 2 and x plus 1. All right, so we're now ready to list our critical points. So let's talk about where they are. So remember, there's two types of critical points at this stage. So in general, there's three categories. And our first category, we've already mentioned, is empty, and that is the boundary. Nothing there. All right, our next category that we'll talk about is where is the derivative equal to 0? So, where does the derivative equal 0? Well, now you think about your pieces. Well, when does x minus 2 equal 0? See, this is why why do we like it factored like this? Because when I set this equal to 0, that says something has to be 0. So, okay, well, that could be when x minus 2 equals 0, which is at x equals 2, or when x plus 1 equals 0, which is at x equals negative 1. All right, now that's certainly true. Now you might want to say, hey, Steve, you skipped something. Be careful, be careful. Now let's talk about the last piece here. X to negative 1/3. When I plug in 0, I don't produce 0. Why not? Well, notice, what's the exponent? It's a negative exponent. So when you have 0 to a negative exponent, that isn't a multiplication of 0. It's a division by 0. So that's not where the derivative equals 0. What is it? That is where the derivative is undefined. All right? So that happens at 0. So therefore, we put all that together, and we end up with 3 critical points. So those are the points which, if we were trying to get our hands on understanding what the function is doing, these would be points that we'd really want to examine closely. All right, good. Well, that's it. All right, we just needed the critical points. And so, time for another problem. Okay. So, find the absolute min and absolute max of the function. H of s is 2s cubed plus 3s squared minus 12s, where s goes from -3 to +2. All right, now, do we know that it has to have an absolute max and an absolute min? The answer is yes. Why? Because this function is a polynomial. Polynomials are continuous, and we have a nice closed bounded interval. So the extreme value theorem says there must be one. So that means we can use our technique. That's our making a list technique, right? So we're going to make our list. Now, I'm going to pause for a second and ask a question. Should we care that our variable name is s? Oftentimes we talk about functions as functions of x, sometimes functions of t. Here we have a function with the variable name s. Is that okay? And the answer is yeah. Look, variables can be whatever we want them to be. All right. Well, so let's proceed. So, making a list. So here's our list. And when we talk about our list, it's our list of critical points where something could happen, an absolute max or min could be found. So you should always just toss in your boundary right at the start. Just they're freebies. So we make our boundary points on our list, -3 and 2. From there, we say, all right, next thing is let's take a look at our derivative. So we'll do our derivative. Let's do it here. So h of s, that's 2s cubed plus 3s squared minus 12s. H prime of s is 6s squared plus 6s minus 12. All right, no surprise, it's a polynomial. We should be good at taking derivatives of polynomials. We want to understand, is this derivative ever undefined? And the answer is no, it's never undefined. Okay, good. Is it ever 0? Oh, well, that's a good question. So let's try and factor. It's a polynomial. We should try and factor 6, then s squared plus s minus 2. And that looks like it could factor. Let's see. I need two things that multiply to -2, but add to +1. So let's check. So that would be what? It would be s plus 2 and s minus 1. So if we set now our derivative equal to 0, we say, aha, we would have -2 or +1. Those are places where our derivative is 0. So they could be on our list. Now you notice I was a little bit hesitant. They could be on the list. We should check one other thing. Because remember, it's not just that our derivative is 0, it's that our derivative is 0 and we need to be in our range of potential values. You see, what if we had said our derivative is 0 at 10? Would we care if our derivative had been 0 at 10? And the answer is no, because we're only looking between -3 and +2. So 10, way out there, we don't even see it. So we got to be careful. So in our case, it turns out that -2 is between -3 and +2, and 1 is between -3 and +2. So we add them to our list. All right, now we've finished our list making process. Now that we've made our list, the next thing is we should sort of double check. Okay, looks good. we got our boundary, took our derivative, life is good. We're going to plug all of these points into our function. So we need now to compute h of negative 3, h of 2, h of negative 2, and h of 1. Now hopefully we'll get things which are reasonable to work with. So maybe, maybe not. So some space for doing some computations here. When I plug in negative 3 cubed, well, it'll be a negative, because if you cube a negative, you get a negative. 3 times 3 is 9. 9 times 3 is 27. And then we double that. So we'd have negative 54. Then we're going to have 3 times negative 3, which is 3 times 9, which is plus 27. And then we're going to get minus 12 times minus 3, which is plus 36. So if we add these all together, 27 and 36 together would add up to 63. Then if you subtract 54, you get 9. So 9. All right. Well, keep going. Plug in 2. 2 times 2 cubed. That's 2 times 8. That's 16. Then we have 3 times 2 squared, which is 3 times 4, which is 12. Then minus 12 times 2, minus 24. 16 plus 12 is 28. 28 subtract 24 is 4. All right, how about negative 2? Negative 2 cubed is negative 8 times 2 is negative 16. The negative 2 squared is 4 times 3 is 12, so it's still positive 12. And then it's minus 12 times minus 2, which will become plus 24. So we have 36 from the 12 and 24 together, minus 16, making this 20. All right, plug in 1. 1 is one of our favorite numbers to work with. 0 is our favorite, but 1 is a good second place. When you plug in 1, really you just need to add the coefficients. So you're going to get 2 plus 3 minus 12. That's 5 minus 12, which is negative 7. All right, so we found our list. We plugged every single value from our list into our function. The last thing for us to do is to now scan our list and say, okay, what's the largest number that we got out? Well, it would appear that the largest number we got out was 20. And therefore, 20 is our absolute max. And if we were after where the absolute max occurred, it would occur at negative 2. Keep in mind that for some functions, you might get the absolute max appearing several times. In other words, you might have the same output, that's the largest, occurring more than once. That's okay. No problem. The smallest output, well, that's the negative 7. All right, so that's our absolute min. And now we're done because we were after the question. What's the absolute max and absolute min? We're going to do a couple of these in our practice, so it's nice to get the pattern. Make a list, check your endpoints, take the derivative. Is it ever undefined? Where is it 0? And plug it in and grab the largest and smallest values. It's a very simple process. And really, what are we testing on? Well, we're really testing on, can you understand how to find critical points? That's the big test. Once you understand how to do that, the rest of the problem is pretty mechanical. So, well, let's do some more practice. Get the mechanics of these problems down. All right, so another problem. Determine the absolute maximum and absolute minimum for the function y equals sine of x minus a half x for the interval between 0 and pi. So what's going on here? Well, the function sine of x, we understand what that looks like. So sine of x normally does something like that between 0 and pi. Goes up and down. On the other hand, what does minus a half x do? Well, minus a half x is a line which looks something like that. You know, it's a line that has a slope of negative a half, and it passes through the origin. So if you put them together, what you're really doing is it's like you're taking your sine curve, your nice sine curve, and then you're going to sort of drag it down. So that roughly speaking, what it should look like is it should do something where, I'm going to do our dotted line for negative, it should look something like the following. It should look something like that. All right, well, that's a rough sketch, and but of course, what are we after? We're after the absolute max and absolute min. Okay, so our process doesn't change. Whenever we see something that says find an absolute max and absolute min, we're always like, make a list. So we start by making a list. We say, all right, throw in the endpoints. They're freebies, but they're also important because the absolute max or absolute min can occur at endpoints. And if you forget them, then you might miss them. So we want to make sure we don't want to miss anything. If you have to err, you would probably want to err on the side of checking too many points, but you really don't want to do that. Our goal is to do the right amount of work. Not too much, but not too little. Just right. Okay, so we've started our list. We have our endpoints. The rest of the points are going to come from looking at the derivative. So next up, we take the derivative. We say, all right, what's our derivative? Y prime. So y prime, derivative, would be cosine of x, then minus 1/2. All right, that's not so bad. Derivative of sine is cosine. Derivative of minus 1/2x is minus 1/2. That's never undefined because the cosine function is a nice function. It's defined for all values, and minus 1/2 will certainly be defined. So it's always defined. So the last thing is to say, well, could it be 0? Well, that would be true when cosine of x is equal to 1/2. All right, well, when does cosine equal 1/2? So if you think about your unit circle, because that's a nice way to think about trigonometry is by the unit circle, the cosine of an angle is the x-coordinate. So when we're saying we want the cosine to equal 1/2, what we're looking at is when does the x-coordinate equal 1/2, which means we're looking for an angle that comes off in one of these two ways. Remember though, we're not looking for all angles where cosine equals 1/2. There's infinitely many angles that do that. We're looking for an angle between 0 and pi where cosine equals 1/2. So there's one angle that does that. 0 to pi is the top half of the circle. So, do we know a nice convenient angle where cosine equals 1/2? Well, this is when studying trigonometry can come in really helpful. And it turns out you can actually get a pretty reasonable sense of what's happening here because this is 1/2. It's the halfway point. That means that this looks like that. So you have a nice little triangle, and you see, oh, that's like a 60-60-60 triangle, right? Equilateral, and it is. And this angle is at x equals pi thirds. So that's our last point on our list. So now our list has 3 candidate points. We've made our list, and we sort of say, okay, do we remember to check everything? Yep, we got our boundary, took our derivative. All right, we're good to go. So the next thing for us to do is plug these into our function. So let's call our function here, I'll call this f of x for our shorthand. So I want to know what is f at 0, f at pi, and f at pi thirds. Well, sine of 0 is 0, 1/2 times 0 is 0, so we keep getting 0. So that's 0. The function of pi, sine of pi is 0, 1/2 pi is 1/2 pi. Don't forget the negative. All right, good. Pi thirds. Well, all right. We said cosine of pi thirds equals 1/2. So sine of pi thirds, that's the square root of 3 over 2. And then we're going to subtract pi over 6, because that's 1/2 times pi thirds. Now, you might be a little bit nervous and say, do we know anything about this value? Well, square root of 3 over 2 is, it's above 0.8. It's larger than 0.8, but pi over 6 is below 0.7. And so this is certainly a positive value. All right, so that's kind of matches with the picture. See, we figured out, look, it's 0, that agrees. Here, that's negative pi halves. So the picture, yeah, it should be a positive value. Now, let's scan our list. What is our largest number? Well, since this is positive, this is 0, and this is negative, our largest is this value. So this is our absolute max, largest value. Our smallest, well, it would be the negative one. And therefore, this is our absolute min. And there you go. We found them. Woohoo! Good. Good for us. All right. Well, one last problem. And this one, it's a true-false. So that's pretty good odds. We've got a 50-50 chance. So a boundary point is always either a local max or a local min. Is that true or is it false? All right. Now we have to dig a little bit here. What is that saying? Well, think about a function here. So I have a function and it's defined. Let's say we go to the right. So what can happen to the right? Well, it seems there's a couple behaviors. It could go up. All right. If it went up, it's a local minimum, yes. It could also go down, but if it went down, it's a local max. Okay. It could go flat. Now we say, aha, maybe this is the secret. See, if it goes flat, does it still work? Well, so let's recap. So this is a local local min. This is a local max. If I'm flat, what am I? Well, I am both a local max and a local min. Now, notice the word or. It has a very technical meaning in math. Or means one, the other, or both. So you're allowed to be both a local min or a local max. So it certainly seems the case, well, look, we're either going up, or we're going down, or we're flat. In any of those cases, our boundary point is a local max or a local min. So yeah, okay, so that's good. All right, so that must mean the answer is true, right? I don't know. I'm suspicious here. Okay, let's think about this. I know they've caught us before. I don't want to be caught again. So, all right, what's going on here? We're trying to understand our behavior at the boundary. We know if our function goes up right away, or it goes down, or it goes flat, then it's a true statement. So, is there another possibility? Could we maybe be going up and down simultaneously? Is that possible? Because if we were going both up and down at the same time, then you couldn't be a max or a min. But at the same time, remember, we only care about what happens nearby. So we'd also have to have somehow, no matter how close we got, we were still going up and down. So is there any function we can think of that has that same sort of up and down behavior, no matter how close you get? Anything? I think we've seen this function before. You remember we've been talking about a function. So there's this beautiful function called sine of 1 over x. It's a wonderful counterexample to a lot of things. And what happens with sine of 1 over x? Remember, it's oscillating, but it starts oscillating more and more frequently until it just goes crazy. Now you can do all sorts of fun things with sine 1 over x. You can, for example, multiply it by x. So it is possible that you can have a function that is moving towards your endpoint, and it's sort of zeroing into a value, but it oscillates more and more often. So an example here we could have is x sine 1 over x if x is not 0, and 0 if x equals 0. Okay? that's a function that has this type of behavior. And notice that if we started at 0, it would be a boundary point. Our function's continuous. Is 0 a local min? Well, no. See, no matter how much you zoom in, there's still infinitely many up and downs happening next to 0, which means there's points that are below 0. Is 0 a local max? No, because you still have infinitely many oscillations. There's infinitely many times you're getting above 0. So it's neither. So this is a false statement. So just because you're at a boundary point does not guarantee you're a local max or a local min. So be careful. Be careful. You have to think, well, what do we actually know? And it's important to understand, do we understand the behavior nearby? In some sense, what we are thinking of is, well, if I can say something about how the derivative of the function is behaving, if it's positive or negative or 0 nearby, that helps me understand what's happening. Here, the derivative, of course, just keeps oscillating wildly between positive and negative. So that's also a challenge. But that sounds like a topic for another session. But anyways, that's the answer for this problem, our last problem for the practice for now. Good stuff. Thank you for coming. Hope you have a great day.